we're going to learn a little bit about some general solutions that we'll use when we solve trig equations. So first, let's consider our parent graph of y equals cosine x. And so hopefully we're fairly used to this, and we'll think about a principal value. So it's a random point somewhere along the curve. Okay, so if you'll notice, here's my point, and I've drawn this horizontal line through it to show that we can have the same y value at lots of different places along the sinusoid. And this goes on forever, left and right, so we technically have infinitely many points with that same y value. We're just calling this our principal value. That's our x value, wherever that y value lies. And so what we want to do is we want to figure out how to name all of the points without having to list them. So the first thing we'll look at, if you notice, this first point that I have is exactly 2 pi or 360 degrees, depending on if you're in degrees or radians, away from not the very next point, but the next on the same kind of downhill. And then if you look again, if we take this point, we go to our following point, it's also 360 degrees away. So we have this series of points that are all 360 or 2 pi away from the previous one. So we want some way to name them. So if we have this point and we're naming it principal value, whatever it might be, theta, x, then this next point here is going to be that same value x plus 360 degrees. Now, there's two sets of 360 degrees or 2 pi's. And so this point over here would be principal value plus not 1 2 pi, but plus 2 2 pi's, or plus 2 360s. And so then we can name each one. The next point would be principal value plus 3 times 2 pi. And then the following one, principal value plus 4 times 2 pi, and so on. And so we'll notice that each one of these is an integer multiple of 2 pi or 360 degrees away from the last. And so we can set up, here's our general formula, right, with 2 pi times 1 times 2 and so on. So if these are all integers, 1, 2, 3, -1, -2, then we can represent that integer with a variable. We'll usually use n to represent a given integer. So next, let's take a look instead of at our principal value, but at the exact opposite, so negative PV. And we'll notice the same thing. This negative PV to the next point is 2 pi or 360 away. And so we can establish the same kind of a ratio or a relationship where we're looking now at this point here is our negative principal value plus 2 pi times 1. And then over here, our negative principal value, so we started at this point, plus 1 2 times 2 pi. Or working backwards, negative principal value, this pink point, plus 2 pi times -1 because we're going to the left. So overall, we can then name, if we're in radians, all of our points that lie at the same y value by starting with our principal value. And they're all in relationship to that one point. So plus 2 pi times, and then n here stands for a given integer. So we can have our other set of points at negative PV plus 2 pi times an integer, whatever that value might be. So that's in radians, and then we also have it in degrees. So that's for cosine. Now let's take a look at sine. Okay, we'll start the same way. We're looking at the parent graph, y equals sine x, and we'll think about a random principal value. And we can see from this principal value, we've got principal value plus 2 pi, and so on, just like cosine. So that first set is going to be exactly the same, sine or cosine. We can have principal value plus 2 pi times n, or principal value plus 360 times n if we're in degrees. Now, the strange thing about sine is our next point isn't going to be negative PV. Negative PV would be over here, right? And that wouldn't give us the same information. It's not the same y value. And so another point that lies along that same horizontal, sorry that this is black, it's not the x-axis. So this next point is no longer just a quick, easy negative PV away. but we can actually come up with its relationship from over here, from the same landmarks. So what I'm going to do is, you see this little dotted box, I'm going to zoom into just that dotted box. So that's what's going on here. That's the zoom in. If we go backwards. Okay, so we're just taking this little piece out. All right, so if we're just going to examine that, our principal value here, this is the y-axis, is this far away from 0. Okay, so it's principal value away from 0, that's that distance there. Well, that's the same distance from where we're crossing the x-axis as this distance over here where we're crossing the x-axis again. So we know this distance and this distance, those two yellow highlighted portions, are exactly the same. And that amount is principal value, whatever that value is. And we also know right here, and this was labeled, it just got covered up by the graph, this value right here is pi. And so if we're looking at this being, this value here is pi. So this point lies exactly pi minus our distance principal value. And so then we can come up with, this point's going to be pi minus PV, or if we were in degrees, it would be 180 degrees minus the principal value. So what we can do is we can use that. So we already have our PV plus 2 pi, PV plus 2 pi times 2, and so on. Now we've got pi minus PV. And then the next one, pi minus PV, that's our starting point, plus 2 pi. And the following one, pi minus PV plus 2 pi times 2. Or we can work backwards. Here's our pi minus PV plus 2 pi times negative 1. And we can go all the way backwards and forwards. So that gives us our sine principal value equations. So our first one is just like cosine, PV plus 2 pi n. But our second one is going to be pi minus PV plus 2 pi n for sine, where cosine, remember, is just negative PV plus 2 pi n. So they're a little bit different. Okay? So we'll look at tangent. We won't go as in-depth, but tangent has its own set. So if we look at the parent graph for tangent, we can see that this time each one of these repeats by themselves. So if we have some random point, so let's imagine we had a point right here, and we wanted to see where the next one is, or actually let's do this one since it's on a line. The next one we can see is right here. Okay, and so what we need to do is say, well, how far apart are these? And if you remember, the standard period for tangent is not 2 pi anymore, it's just pi. And so each one of these little s's repeats every pi. So you see this point here on the 0, the next one on the 0 is pi, so that's exactly pi away. So this point here, the next one is going to be that point plus pi. So we don't have to worry about two sets of equations this time, and the distance between each of our points is just going to be pi instead of 2 pi like sine and cosine. So then when we look at our general solution equations for tangent, we just have one. Okay, so we're just looking at our principal value and adding pi times, again, that n represents some integer value. Could be positive, could be negative. If we're in degrees, remember the degree equivalent of pi is 180. So we have in degrees principal value plus 180 times n, in radians principal value plus pi times n. So there you go. Those are our general solution equations that we'll use when we solve trig equations.